Good morning, everyone. Myself, Umapriya from Erode Sengunthar Engineering College, Tamil Nadu. Today, in this session, specially planned for the AICTE Prerana stream. Under this stream, we are made this presentation to help the SC/ST students for their higher education preparation. Especially for the GATE preparation, we planned this session particularly to help the SC/ST students under the AICTE Prerana stream. And in this today's session, we are going to discuss a particular topic, conduction, in the heat transfer subject. In chemical engineering field, we all well known about the heat transfer. Particularly, we have three kinds of transport processes. One is momentum transport, second one is heat transport, and third one is mass transport. In this specifically, we are having the specific subject for the heat transfer. In this subject, we'll discuss about the how the heat is flowing and each and every point how the heat flux it is varying and at each direction how the variation it is showing. Okay, and what are all the analogies we have to relate the heat transfer and mass transfer also. And in this, initially, we'll discuss about the mode of heat transfers, and that particularly in this session today specifically we are going to concentrate on the conduction mode. Okay, before going into this session, first in a brief, we'll discuss about what is heat transfer and what are all the different modes of heat transfers we have, and particularly how the conduction it is varying from all other kinds of modes, and in conduction itself what are all the law we are using and how we can use that particular law to solve the problem to find the heat flux and to find the temperature at the inlet point and outlet point, and how we can find the thermal conductivity. Okay, because we all well known about the thermal conductivity, it will change for each and every material. So all the concepts we'll discuss in this session. Okay, so first one is heat transfer. What is heat transfer? In the name itself we can easily find out. Heat is transferring from one medium to other medium, from one place to other place, right? So heat generally we will mention in the form of energy. Here also we have mentioned the same thing. Heat transfer, it is the transfer of energy due to temperature difference in a medium or between two or more media. In a single medium itself, that energy transformation can occur, or two or more media can take part in the transfer of energy. So that is the thing here we have mentioned. Transfer of energy, that is nothing but the transfer of heat. The heat generally it will form due to the temperature difference. Generally we all know about there will be the high temperature medium and low temperature medium, especially where the temperature difference it will occur from the higher temperature to lower temperature medium only, right? The transfer it will occur from the higher temperature medium to lower temperature medium. So this is the concept. So heat transfer, it is the transfer of energy. It will occur due to the temperature difference in a medium, maybe a single medium, or between two or more media. Okay, so while discussing this itself, we can find what is the driving force behind the heat transfer, right? So generally, what is the driving force? In the discussion itself, we can particularly mean temperature difference, it is the driving force, right? So only we are calling driving force for the heat transfer is temperature gradient. Temperature gradient means what? That change in temperature with respect to the length of the along the path of the pipe or system, whatever it may be, right? So the same thing, heat transfer rate. Here we can denote the symbol Q, capital Q. We have two symbols, one is capital Q and the other one is small q. what is the difference between the capital Q and small q, because most of the time we'll do the blended mistake in this capital Q and small q only. Capital Q is nothing but your rate of heat transfer or heat transfer rate. Q is heat flux. Okay, got it? And here, heat transfer rate. Rate itself, it denotes the change in that particular property or the quantity of that particular property with respect to your time, unit time, right? So volumetric flow rate, we all know about the volumetric flow rate is nothing but volume with respect to your unit time, how much volume it is flowing in that particular system per unit time. Same like this mass flow rate, how we can define how much the mass is passing per unit time at that particular point, right? So here also heat transfer rate, how much the heat is passing per unit time. Okay, so that is nothing but your small, capital Q. And here the capital Q, it can be written in the form of small q into A, because small capital Q is nothing but heat divided by time, right? So this time it can be modified with the Q into A, because Q is heat flux. Flux means what? The quantity passing per unit time per unit area, right? So here also heat flux, the how much heat is passing per unit time per unit area. So Q, that is nothing but capital Q divided by T into A. So if we cancel this A, definitely we'll get the heat transfer rate only, right? So capital Q is can be written as small q into A. Here the small q is nothing but your heat flux. This A is nothing but your heat transfer area. Okay, whatever the system we may take, it may be the pipe or cylindrical wire or whatever it may be, or nuclear section or whatever it may be, the thing cross sectional area is nothing but your capital K. So this is the relationship between the heat transfer rate and heat flux. So heat transfer rate is equal to heat flux into cross sectional area. Okay, and here Q, it can be written in the unit of watt, because we use SI unit. Here also Q, for the Q we are using the watt as the unit, and we have to maintain this watt only while solving the problem, otherwise we will get the variations in the answers. Okay, you just all keep in mind, we have to maintain the watt unit only while solving the problem for the capital Q rate of heat transfer. And same like this for the heat flux, we have to maintain the watt per meter squared. Okay, watt per meter squared we have to maintain. If we have centimeter in the term of centimeter or millimeter, whatever it may be, we have to convert that cross sectional area to meter. Then only we can write we'll get the correct answer. Okay, then area, we have to change that one to meter only. Okay, then generally we all know that heat is always transferred in the direction of decreasing temperature. It shows that generally heat it will transfer from the higher temperature to lower temperature. Then one more thing, if the heat is transferred from one place to other place or one medium to other medium, from that medium where the heat is transferring, right, that medium heat, definitely it will keep on decreasing only. This is the sentence, it is showing the concept. Heat is always transferred in the direction of decreasing temperature. Okay, then what is the difference between the temperature and heat flux? Because we'll use temperature term also while deriving or while solving, and we'll use heat flux term also, but the concept behind the temperature and heat flux more or less same only, right? Where it is differing means temperature, due to the temperature difference, how much the variation it will occur, that is nothing but your heat. So heat, the temperature is a plain scalar parameter. Okay, so we'll get 25 degrees Celsius, 35 degrees Celsius, 305 Kelvin, 100 Kelvin, like that, we'll get a proper value for the temperature. We'll not get any effect with respect to the directions of the heat flow. Okay, it may be the X direction or Y direction or Z direction. It does not reflect in the temperature value. Okay, definitely we'll have the temperature in the scalar quantity only. Initial temperature we may have and final temperature we may have, but all the terms it will be in the same direction only. Will not get any deviations with respect to your vector quantity. But heat flux, it will, we can't write as like your temperature, because heat flux, that flux term itself, heat flux term itself, it is showing how the heat is flowing and on which direction. Okay, so it may be in one direction, or it may be in two directions, or it may be in three directions, right? So only while writing the Q term, we'll mention Qx, Qy, Qz, like that we'll mention, because heat flux generally it gives the impact based on your, it shows the impact based on the directions of the heat flow. So only here also we have mentioned heat flux is a vector quantity. So Qx, Qy, Qz, it just resembles the sentence heat flux is a vector quantity. Okay. Then next one is how the heat transfer it is varying from the thermodynamics. Okay. We all well known about the thermodynamics concept, and we are studying the heat transfer concept also. Then how the both terms they are differing, because in thermodynamics also we'll discuss about the temperature and heat, internal energy, entropy, enthalpy, whatever it may be. And heat transfer also we'll discuss about the Q, temperature, small q, and del H, everything. Okay, and in which point both the subjects are differing. Okay, we are getting a what is that? Routinely this kind of questions in our mind, because we are studying thermodynamics and heat transfer, and in which point both the subjects are differing. So all of you must know that the thermodynamics, definitely it will, this subject it will be running behind the system. Okay, system surrounding. So system surrounding means thermodynamics, it will show how the heat is transferred. Okay, how the heat is transferred from the lower temperature to higher temperature, or from the higher temperature to lower temperature, or in the cyclic form, or reversible form, or irreversible form. This kind of process concept only we can come to know from the thermodynamics. But in the heat transfer, we will discuss about the transfer of heat only. Okay, same like what thermodynamics, we'll discuss about the transfer of heat only. But in which point that heat transfer is varying means in which mode it is transferred. Okay, with the help of which mode the heat is transferred. So we have first, to solve this, we have to clear in the mode of heat transfer. Okay, we in this session we are going to discuss about that one also. So heat transfer, it is differing from the thermodynamics in the term of mode of heat transfer. Okay, so this is the main concept. And second point, how much work is done, it can be given by the thermodynamic subject. Okay, and here we'll see work is done by the system or work is done on the system. Okay, based on that we'll give minus W and plus W. So thermodynamics, it will give how much work is done on the system or by the system. But here in heat transfer, okay, same like this, heat transfer only. Here also, what rate of heat transfer transformed. So that point only we'll discuss. We will not discuss about the work point of view. Okay. So by thermodynamics, definitely to close the process, we have to mention the work also, because the first law of thermodynamics, it is showing that energy in is equal to energy out. Law of conservation of energy. There is no energy can be created and destroyed also, right? So the heat formed or heat got it from one body, definitely it will transform to another form of energy. So only we are discussing and we are going to give the conclusion with the help of the work. But in heat transfer, definitely we'll discuss about the rate of heat only, will not go beyond that one. Okay. And in thermodynamics, we'll discuss about the initial and final state of the system. Okay, but in heat transfer, we'll discuss about the temperature distribution in each and every point inside the body or outside the body or whatever it may be. We'll discuss about the temperature distribution. Here, Ti, T naught will discuss, right? Here, Ti, T naught, T1, T2, T like that. In each and every point, how the temperature variation it is occurring. We'll discuss in the heat transfer specifically. These are all the main differences between the thermodynamics and heat transfer. Okay, in thermodynamics we'll discuss about the entire process, we'll finish the process fully thoroughly. But in heat transfer we'll discuss about the system, how the heat is transferring from the system or on the system or inside the system, and on which mode it is transferring, and temperature distribution, how much varying inside the body. Okay, how it is differing inside the body at each and every point. This is the main concept. So everyone can say that heat transfer, definitely it shows the clear picture in the heat transfer only. How much heat is transferring, how temperature is varying. That is the only concept we are running behind in the heat transfer. Okay, and different modes of heat transfer processes. We have three modes of heat transfer processes. One is conduction, second one is convection, third one is radiation. So while seeing, we can say that all the things are modes of heat transfer only. But while studying each and everything, it is showing the different concepts, because heat is transferring. That is the basic concept, same concept here in conduction, convection, radiation. But how it is transferring, in which medium it is transferring, while transferring, what is the thing it is giving that it is pushing that transfer. So these are all the things. Okay, blendedly it is differing in each and every modes of heat transfers. Example, in conduction, heat is transferred due to temperature difference only. Here also in convection, radiation, all the things are due to temperature difference only, temperature gradient only. But see here, the next point itself, in a stationary medium or media. Okay, in a stationary medium or media. Yeah, okay, so stationary medium, so that medium, it should not flow anywhere. It should not move anyway. Okay, that is the main condition for the conduction. Okay, but inside that medium, it may be the molecule or atom or whatever it may be, that will move. So due to that movement only the conduction will occur. Okay, so heat transfer is due to a temperature gradient in a stationary medium or media. Conduction needs matter and does not require any bulk motion of matter. So this is the concept what I said already. Bulk motion, it should not be there for the matter, but inside the matter, atoms, molecules or electrons or whatever it may be, it can move. Due to that motion only, the heat will transfer inside the body, or it will transfer from the one end of the body to the other end of the body. This is the conduction process. And convection, again, this is also due to the temperature gradient only, but between a surface and a moving fluid. Here, while discussing itself, we can clearly say that conduction, it will occur in the solid medium. How we are only telling that solid medium we'll discuss later in the forthcoming slides. Okay, and convection, definitely the heat transfer, it will occur due to the temperature difference only, but between a surface and a moving fluid. Okay, so main concept is the heat will transfer in the moving fluid, but a fluid, definitely it will come and touch the surface, solid surface, right? So only it is the combination process. Definitely wherever the convection process is there will be their conduction process also will be there. Okay, so only we are mentioning a surface and a moving fluid. Okay, then last concept, radiation. Here also the heat transfer it will occur, but due to the emission of energy in the form of electromagnetic waves by all kind of bodies. Okay, all kind of bodies, but particular temperature is above the absolute zero temperature. That body it should be above the absolute zero temperature. So normally here, okay, here we can get the radiation from the sun, and we can get the radiation from the UV lights. So so same like this, for this conduction and convection, we should have some matter to or medium to transfer the heat. But in radiation, we no need of having any matter or medium to transfer the heat from one place to another place, because this is an electromagnetic wave, right? So in between, no need of having any matter, because it will pass through that one, or whatever the matter it may be, it will pass through that one and it will reach the point. Okay, so only the radiation, the heat transferred due to the radiation, it gives the biggest and largest impact in the environment. Okay, conduction and convection, it will not show much impact in the environment, but the radiation we can't see, but definitely the impact it will be high. Okay, in this session, in this conduction, convection and radiation, specifically we are going to concentrate on the conduction process. Okay, as discussed earlier, what is conduction? Conduction, it is the transfer of heat due to the temperature gradient only, due to the formation of temperature gradient only, but inside the matter. Okay, and here also the same thing we have mentioned. See, it is the transfer of energy due to either random molecular motion or due to the motion of free electrons. Okay, so the body, it should be in rest condition, it should not move anywhere, it should not have any motion, but inside that body definitely it can be packed with a number of molecules and number of electrons and number of atoms, right? So there may be the movement, may be there. Okay, that movement only it gives the conduction process in the heat transfer. Okay, so only we are particularly mentioning solid is the medium where the conduction process can easily occur. How we are mentioning solid is the medium for the conduction process specifically means, see here I have mentioned the reasons. Okay, so first thing, it is due to the either random molecular motion or motion of free electrons, we came to know. And how particularly we are mentioning solid only means, see here, gases. Okay, gases we all well known about, it is the medium with the help of your randomly moving molecules, right? So while giving the conduction process, okay, while giving the conduction process, it is due to the collisions of randomly moving molecules, right? So definitely the conduction process, it will not give much variations. Okay, much variations, because here particles are moving. Okay, particles, that body itself moving, right? That body itself moving, flow is there. But here the basic condition for the conduction is the body, it should not have any motion. But here the molecules are loosely packed, so definitely that system itself, that body itself, it is having the motion. So gases we can't consider in the conduction process, and liquids same like your gases. Here the liquid also having the same thing, it is also having the mean free path. So the system, the liquid system, it is having the free motion in that. Okay, when compared to gases, it has some limitations, liquid, but definitely it is also having the free path of motion. So only we are not considering the liquid also as a medium in the conduction process. Then last one is solid. Okay, why I have mentioned the solid in the last sentence means, because if we come to know the gas and liquid problem, definitely we can say that solid is the only medium to conduct to transfer the heat from the mode of conduction. Okay, so then solid again, it is the tightly packed medium, and solid it will not have any motion. So definitely this solid only the medium to have the conduction mode of heat transfer. Okay, here see, conduction is due to lattice vibrations and or motion of free electrons, but not the motion of body. It is the due to the motion of free electrons. So the solid is the only medium we can use the to transfer the heat with the help of conduction mode of heat transfer. Okay, then next one is in solid bodies, conduction is the significant heat transfer mechanism because no material is flowing in this process, already we discussed. Then what is the law we can use for the conduction mode means we have Fourier's law of heat conduction. Okay, Fourier's law of heat conduction. Fourier, he mentioned he suggested one law for the heat conduction process, and in this he denoted that heat transfer rate is directly proportional to the temperature gradient. Yes, definitely the temperature gradient value, if it increases, definitely the heat transfer rate is also will increase. Okay, that is the thing here we have mentioned. Heat transfer rate is directly proportional to the temperature gradient. Okay, dt by dx is the temperature gradient. So here I have mentioned dt by dx, and here this is proportional. These two things are having the proportionality, right? So to cancel that proportionality, we are giving the constant. So that proportionality constant is k here. Okay, and in this k also, it is nothing but transport property of that particular material. Okay, we are giving the proportionality constant only, but that proportionality constant itself, it is showing the transport property of that material. Okay, so what is k? What is k? We all know about the k is nothing but the thermal conductivity of the material. Conductivity means what? The capability of the material to what is it, transfer the heat in the body. Okay, so this is the k. Okay, so only we are mentioning k is the transport property. In the name itself, thermal conductivity, how the heat is conducting, how the heat is conducting through that particular body, that is nothing but your thermal conductivity. So based on the thermal conductivity only, we are differentiating the material as a conductor, semiconductor and insulator. Okay, so based on this particular concept, thermal conductivity, we can tell that conductivity, conductor, semiconductor and insulator. Conductor means that material, it will conduct the heat abundantly. Okay, so without any hesitation, it will transfer the heat. That is the conductor. Semiconductor, definitely it has some restrictions. In that particular material, it has restrictions. Okay, it will help to pass the heat from the body to from the one end to another end, but it has some limitations. So the efficiency of that particular material, it will not be that much high. So only we are giving the name as semiconductors. Sometimes it may act as an insulator also, but insulator particularly 100%, it will not have the any conducting of the heat. Okay, so only we are naming it as insulators. So this thermal conductivity, based on this one only, we can classify the material as conductor, semiconductor, insulator. So in the thing itself, in the discussion itself, we can say that each and every material, it has different value of thermal conductivity. Example, copper is having the different thermal conductivity, iron is having different thermal conductivity, wood is having different thermal conductivity, plastic is having different thermal conductivity. So we all know about the iron and copper, it has the higher conductivity, right? So only conductors. Wood, definitely it will not allow. Plastic, it will not allow. So only those things are insulators. Okay, and from this statement, we can say that rate of heat conduction is directly proportional to area into temperature difference divided by thickness, right? So temperature difference divided by thickness is nothing but your temperature gradient. So to cancel this, we are introducing the proportionality constant k, thermal conductivity. See here, mathematically we have expressed q is equal to minus k into a into dt by dx. If we know, we all discussed about the q by a is nothing but small q heat flux. So heat flux Q is equal to Q by A is equal to minus K into dt by dx. Clear? Then next one is, I think after this immediately we can discuss about the problems, because these are all the main topics we'll get in the syllabus. Okay, so up to this, if we know thoroughly, definitely we can attend the minimum question in the heat transfer. Okay, so these are all the problems. Here I have mentioned some of the problems based on the conduction concept only. So to solve this problem, first thing we have to know what is conduction, okay, what is thermal conductivity, and for each and every material how the thermal conductivity it is varying. Okay, so based on this we may have the theory question, and second one is we have the law to related to your conduction, that is Fourier's law of heat conduction. In that Fourier's law of heat conduction we have small q is equal to minus k into dt by dx. Okay, and capital Q is equal to minus ka into dt by dx. So each and every term abbreviation we should know thoroughly. Capital Q means rate of heat transfer, small q is heat flux, dt is nothing but temperature difference, dt by dx is nothing but temperature gradient, k is thermal conductivity, and for all the terms we should know the units also very clearly. Then okay, we can come to the problem point. Definitely we can easily solve the problem if we well known about the theory part of the conduction. Okay, see, first question is, consider steady state heat conduction across the thickness in a plain composite wall. Okay, composite wall we all known about. Composite wall is nothing but the more than two material it will be there, that is nothing but the composite, right? So in this also they have shown, see, two walls we have, two materials we have. Okay, that is the composite wall. As mentioned in figure, we have two materials exposed to convection conditions on both sides. Why here they have mentioned convection means, see, outside we have the fluid motion only, right? So only they have mentioned convection, but the problem what they are asking inside the system only, so that is nothing but the conduction. Okay, and this convection if we use, we have one more formula also, that is Newton's law of cooling, that gives Q is equal to HA into del T, HA into del T. The same thing here also we will use. Okay, conditions on both sides. Once again I repeat the question, consider steady state heat conduction across the thickness in a plain composite wall. Okay, as shown in the figure, exposed to convection conditions on both sides. So both sides we have convection condition as mentioned here, and here they have given the data. See, HI. Okay, individual heat transfer coefficient at the entrance point. Okay, HI is equal to 20 watt per meter square Kelvin. H naught, again individual heat transfer coefficient. Okay, at this your exit point, H naught, 50 watt per meter square Kelvin, and the temperature at the entrance point is 20 degrees Celsius, and the temperature at the exit point is minus 2 degrees Celsius. So the temperature while touching the solid body it is 20 degrees Celsius. After passing through this, while reaching the exit point, it reaches the minus 2 degrees Celsius. That is the thing here they have mentioned. And K1, for K1 is nothing but the thermal conductivity of the first material. Thermal conductivity of the first material. This is the thing. For first material, it is having the thermal conductivity 20 watt per meter Kelvin. K2 for the second material. K2 it denotes second material thermal conductivity. K2 is 50 watt per meter Kelvin. And here based on this figure given, L1 is 0.30 meter. L2 is 0.15 meter. Okay, L1 is 0.30 meter. L2 is 0.15 meter. Check all the things are in the SI unit or not. If not, you have to convert the unit to SI unit. Okay, so here watt per meter square Kelvin, it is in the SI unit only. Here watt per meter Kelvin, this is also it is in the SI unit only. Meter, again this is also in the SI unit only. Here check 20 degrees Celsius, 2 degrees Celsius. So again we have to change its degree Celsius to Kelvin. Okay, degree Celsius to Kelvin. If we take 20 degrees Celsius plus 273, we'll have 293 Kelvin. Then here 273 plus if we do, we'll have 271 Kelvin. And no need of what is the converting this degree Celsius to Kelvin also, because in problem formula, if we have only temperature difference, we no need of changing anything, because difference between in the term of degree Celsius and difference in the term of Kelvin, both the thing it will give the same value only, because for all the things, okay, converting to Kelvin, we are adding 273 Kelvin only. So whatever the change we have, the change is common, right? So it will not give any change while taking the temperature difference. So these are all the data they have given. Okay, and assuming negligible contact resistance between the wall surfaces. So between the two wall surfaces, there will be the contact resistance, but that is negligible here. They have mentioned very clearly. The interface temperature in T degrees Celsius of the two walls will be. So what they are asking, see here, interfere temperature. Okay, intersect temperature. See 1 and 2, it has specific intersect point, right? That intersect point, okay, intermediate point is having a specific temperature. That temperature point only we have to find it out. Here they have named it as T degree Celsius. So here they are asking the result also in degree Celsius only. Okay, so we have to keep in mind that one also, degree Celsius only. And we all known about the resistance formula for all the things. If we consider convection and conduction, we have to write all the terms only. Okay, so resistance is equal to 1 divided by H1A. This H1A is for convection point of view in the fluid system at the entrance point. Okay, H1A into dt only we have, right? Same thing only here also we are writing. That resistance value only we are checking. D1, T1 minus T2 only we are checking. So 1 divided by H1A for entrance. The same like this, we will have 1 divided by H2A for exit point. Okay. And in between for each and every material, for both the materials, we will have L1 divided by K1A, because this is your dx, right? So dx, this is dt only. So dx is nothing but your L1. See, check here. L1, this is the x1 and x2 means x2 minus x1, that is nothing but L1. Here x3, x2 means this is x3 minus x2, that is L2. So only here also we are using L1 directly. L1 divided by K1A plus L2 divided by K2A. And in all the terms, A, cross-sectional area of heat transfer is same. So only we are taking this 1 by A outside as a common value. And the remaining things are 1 divided by H1 plus L1 divided by K1 plus L2 divided by K2 plus 1 divided by H2. Okay, from the given data, if we substitute H1 value 20, L1 value 0.30, and then K1 value 20, then L2 value 0.15, K2 value 50, then H2 value 50. If we substitute all the things, okay, while solving, we'll get 0.088 value divided by A. Okay, and one more thing, we can write Q2 terms in terms of temperature difference as T1 plus T2 divided by R equal to, again this can be equal with T1 minus T divided by 1 divided by H1A plus L1 divided by K1A. Okay, if we substitute all the terms in this, see REQ already we have found it out. The 0.088 divided by A. So T1 plus T2, that is nothing but our 22. Okay, T1 plus T2 is nothing but your 22. See here this 20 and here this is 2. So 20 minus of minus 2 will have plus 2. So 22 divided by 0.88 divided by A equal to T1 minus T divided by 0.065 divided by A equal to 22 into 0.65 divided by A will have, and T1 is 293 minus T. If you substitute all the terms, we'll get T value is 3.75 degrees Celsius. This T is nothing but our intermediate temperature. Okay, for the both the two materials, it will have the intermediate temperature is 3.75 degrees Celsius. So here see the options: minus 0.5, 2.75, 3.75, 4.5. In this, the answer 3.75 is there. So the answer option C is the answer. Clear? Then next question. I think you all came to very clearly this first question. There is no doubt in this, I hope so. And we'll go into the second question. This is the second question. Okay, for a given heat flow and for the same thickness. Okay, for a given heat flow and for the same thickness, the temperature drop across the material will be maximum. Across the material will be maximum for. Okay, here they have mentioned different materials. One is copper, steel, glass wool, and refractory brick. And in this, they are asking, okay, the temperature drop across the material will be maximum for. Will be maximum for. Where it will be? Okay, where it will be, we have to find out. See, before going into the discussion point, while reading the question itself, we can find the answer. Temperature drop. Temperature drop, if it should be the maximum, definitely you just tell whether it is the conductive material or insulating material. Yes, think. Yes, definitely it should be the insulating material, right? So here see, copper, steel, glass wool, and refractory brick. Before going into the conceptual discussion, okay, theoretical discussion, we can practically say that, okay, which one it is having the insulating capacity, okay, insulating character. So this glass wool is having the insulating character when compared with all other things, right? Okay, so that is the answer. But while showing in the theoretical point of view, we all well known about the Q is equal to minus Ka into dt by dx, right? Q into dx divided by A is equal to K into dt. If we tell that this thickness is same for all the things, okay, this thickness is same for all the things, definitely heat flow and thickness are same. Means this, or this is the term, it is constant for all the things, right? So K dt, it will become constant. Okay, so if we rewrite this dt, it will become 1 by K. Okay, so we can say that, and we all know that the temperature difference is directly proportional to your inversely proportional to your thermal conductivity, right? So the same thing only here also we derive. dt is directly proportional to 1 divided by K, or otherwise dt is equal to constant divided by K. If we remove the constant, definitely we have dt is directly proportional to 1 by K. Okay, this is the thing here also I have mentioned. The thermal conductivity will be minimum where the maximum drop occur, or the maximum drop will occur where the thermal conductivity is minimum. So the question is, the temperature drop across the material will be maximum for, okay, the thermal conductivity minimum. Thermal conductivity minimum means that is nothing but the insulator. So this is the answer. Option C is the answer for the second question. Then we'll move on to the question number 3. In descending order of magnitude, the thermal conductivity of, okay, in descending order of magnitude, we have to write it. The thermal conductivity of the material. Okay, so first material, what they have given, pure iron. Okay, the second material, liquid water. Third material, saturated water vapor. And fourth material, pure aluminium. Okay, and they are asking descending order. Okay, they are asking descending order. So we have to first think of this descending order. So pure iron, liquid water, saturated water vapor, and pure aluminium. Okay, thermal conductivity is the basic thing. We are going to match this, right? Map this. So which one is having the thermal conductivity, higher thermal conductivity in this 4 materials? Check. This pure aluminum, yes, definitely this pure aluminum, it is having the higher thermal conductivity. Then next thing what it will come, pure iron it will come. Okay, metal. So pure iron it will come. So first thing D, okay, and second thing is A, and third thing definitely liquid water, because the last one is gaseous condition only, right? So the third one is liquid condition, fourth one is gaseous condition. Okay, so the if we map this, definitely the option C it is mapping. Okay, D, A, B, C, pure aluminium, pure iron, liquid water, and saturated water vapor. Okay, so the answer for this question number 3 is option C. Clear. Then we are moving into the fourth question. Okay, a copper block and an air mass block having similar dimensions are subjected to a symmetrical heat transfer from one phase to other each block. Okay, the other phase of the block will be reaching to the same temperature at a rate. At a rate. See, first one is copper block, right? And air. So we all well known about the copper block only. In copper block only, the transformation it will be high. The same thing only here also they are asking. The other phase of the block will be reaching to the same temperature at the rate. So for both the thing, other phase we have to reach it. Okay, which one it will reach very fastly? In copper block only, because it is having the higher thermal conductivity. So check the answers. Faster is in air block, faster in copper block, equal in air as well as copper block. Cannot be predicted with the given information. No, we can predict the information, and we can't say that equal amount in the air and copper block. No, never. So air block is your gaseous block, so never when compared to a solid. So copper block is the answer. Faster in copper block. Option B is the answer for the question number 4. And if we move to the question number 5, a plain wall is 25 centimeter thick with an area of 1 meter squared and has a thermal conductivity of 0.5 watt per meter Kelvin. If a temperature difference of 60 degrees Celsius is imposed across it, what is the heat flow? Okay, what is the heat flow? A plain wall they have mentioned here, right? A plain wall they have mentioned here. So 25 centimeter thick they have mentioned, right? So dx is 25 centimeter. Dx is 25 centimeter. We have to change that one to meter. So 0.25 meter we will have. With an area of 1 meter square, meter is there, so we can keep as it is. And area A is 1 meter square and has a thermal conductivity K, small k is 0.5 watt per meter Kelvin, and the temperature difference across this is 60 degrees Celsius. So 60 degrees Celsius, if we change this one to Kelvin also, again 60 only the difference, because here they have mentioned the temperature difference only. Okay, so temperature difference of 60 degrees Celsius, we can take dt is 60. Okay, is imposed across it. What is the heat flow? So if we substitute in this formula, Q is equal to Ka into dt by dx. Okay, Fouriers law of heat conduction mathematical expression. K is 60 into 0.5 into what is that? 1 into 0.5 into 1 into 60. Here will not have 60. 0.5 into 1 into 60 divided by 0.25. We will have 120 watt. We will have 120 watt. So that is your Q value. See, A is the option. A is your answer. For the question number 6, option A is the answer, 120 watt. Okay, so Q is equal to K. K is 25. Sorry, K is 0.5 and A is 1. So 0.5 into 1 into 60 is your temperature difference divided by 0.25. We will have the 120 watt is the answer. Okay, and the next question. A stagnant liquid film of 0.4 mm thickness is held between two parallel plates. The top plate is maintained at 40 degrees Celsius and the bottom plate is maintained at 30 degrees Celsius if the thermal conductivity of the liquid is 0.14 watt per meter Kelvin. Okay, so K value given 0.14 watt per meter Kelvin, and first initial is 40 degrees Celsius and bottom temperature is 30 degrees Celsius. The temperature difference what we'll have 40 minus 30. See here dt 40 minus 30 will have 10 degrees Celsius. Okay, and if we convert this one to Kelvin also we'll have the 10 Kelvin only, and divided by this thickness value what they have given 0.4 mm. So if we convert this one to meter, 0.0004 meter we'll have. Okay, if we substitute all the values in the same formula, because here what they are asking, here also they are asking the heat flux value only. Okay, heat flux value only they are asking. Okay, so here Q is equal to K into dt by dx. If we substitute all the things, what will be the value? 3500 watt per meter squared we'll have. 3500 watt per meter squared we'll have as a heat flux. Okay, heat flux, steady state heat flux only they are asking. So Q is equal to 3500 watt per meter square. Here the option C, it is there 3500. So option C is the answer for this question. Then next question, heat flux across an insulating wall with the thermal conductivity K is equal to 0.04 watt per meter Kelvin and the thickness 0.16 meter is 10 watt per meter squared. The temperature of the inside wall is minus 5 degrees Celsius. The outside wall temperature is. Okay, so here thermal conductivity they have given K is equal to 0.04 watt per meter Kelvin, thickness 0.16 meter, we got it. And here see the heat flux value only they have given, heat flux across an insulating wall. So heat flux is 10 watt per meter squared. Okay, heat flux value they have given. Now what they are asking, the temperature of the inside wall is minus 5 degrees Celsius. Outside wall they are asking. First, before going into the finding of this outside wall, we have to find the temperature difference, right? Then only we can find the outside wall. T1 minus T2 we have to find it out. Then after this, if we substitute this minus 5 in that, then only we can find the outside temperature, right? So the formula, same formula only, Q is equal to K into dt by dx. Here we have to find the dt, del T value. So del T is equal to Q into dx divided by K. Q value is 10, okay, into dx value is 0.16 divided by K is 0.04. So here also we have written 10 into 0.16 divided by 0.04 equal to, okay, equal to what is the thing we are getting while solving this? 40 degrees Celsius we got it. Okay, 40 degrees Celsius. This is the temperature difference. Okay, this is the temperature difference T1 minus T2. T1 minus T2 we got it as 40 degrees Celsius. If we substitute this in that same thing T1 minus T2, we can find the unknown temperature, right? If we can find the unknown temperature. If it is T1, T2 is, we have to find it out. Therefore, the outside temperature minus 5 plus 40, it will give the 35 degrees Celsius. So check where the 35 degrees Celsius, it is there in the result, given results. So it is there in the option C, 35 degrees Celsius. So for this question, option C is the answer. Okay, 35 degrees Celsius is the answer. The next question, we'll move on to the next question. A composite wall of a furnace is made of two materials, A and B. We have two materials, composite wall. The thermal conductivity of A is twice that of the thermal conductivity B. So K, okay, K of B, above K of B, it is 2K of B is nothing but the K of A. Okay, K of A is 2K of B. While the thickness of the layer A is half of the B. The thickness of A, X is, okay, X is half of the B, 1/2 of XB. if the temperature at the two sides of the wall are 400 and 1200 Kelvin. Okay, T1 and T2 given. We can find the del T value. Then the temperature drop across the layer of material A. They are asking temperature drop only for the material A. Okay, same thing, we can solve the same kind of formula only. Q is equal to minus K into dt by dx. If we substitute these things, this Q value it will be same only, right? Q value it will be same. Based on this concept, I am equating the things 1200 minus 400 because we know the temperature difference divided by L divided by 2 by 2K because the relationship between the A and B material for the thermal conductivity and distance already we have discussed. So I have substituted all the things here. L by 2 divided by 2K plus L by K. So it should be equal with del T1 divided by L by 2 into L by 2 divided by 2K. Then if we substitute all the values, this LK it will be automatically get cancelled. Then 800 divided by 5 only I got it. Okay, so if I solve this, I got 160 Kelvin. So here in option D, the answer is 160 Kelvin. So the answer for this question is option D, 160 Kelvin. Then we'll move on to the last question. For a given ambient air temperature with increase in thickness of insulation of a hot cylindrical pipe, the rate of heat loss from the surface would. Okay, for a given ambient air temperature with increase in thickness of insulation, we are increasing the thickness of insulation of hot cylindrical pipe. Okay, the rate of heat loss from the surface, the rate of heat loss from the surface. See, check, it definitely it will decrease. It will decrease. Okay, so option A is the answer. How we are saying this? It is decreasing. How we are saying this? This is decreasing mode. Okay, if the critical radius is less than your outer radius. Okay, if the critical radius is less than your outer radius, if we keep on increasing the thickness of the insulation, definitely it will decrease the heat loss only, right? Practically we can tell the answer, no need of searching all kind of theory point of view. So we can tell this answer in the practical view itself, because if the critical radius of insulation is less, okay, when compared to your outer radius of pipe, if we are increasing the thickness of the insulation, okay, while increasing the addition of the insulation thickness, definitely the heat loss it will be decreasing only. Okay, the option A is the answer for this question. Option A is the answer for this question. Okay, so I hope you all understood this session very well. Okay, it will be more helpful for your gate preparation also. Okay, and from this session we came to know about the clear theory aspects of the conduction mode of heat transfer, and based on this we have gone through some problems. We have gone through almost more 9 to 10 problems, and hope so you all understood this concept and problems concept also. Okay, once again I thank AICTE Prerana. This is the scheme mainly planned for the helping for SC/ST students for their higher education preparation. Okay, we are very happy to stand behind this, and once again I thank AICTE and all the platform who gave this opportunity, and thank you one and all present here. Thank you.